Hi everyone, as Mike's just said, I'm Andrew Drage. I'm a materials engineer and technical consultant for Copper Development Association. And my subject today will be the corrosion behaviour of metals in seawater, with the subject matter being based on detailed information from two colleagues, Carol Powell and Mark Turr. And it will cover many materials and corrosion properties that will hopefully be beneficial to you all. So without further ado, the corrosion behaviour of metals in seawater, marine corrosion, seawater corrosion is down to a complex combination of properties and conditions with different groups of materials performing in different ways dependent on circumstances and environment. Understanding the differences in seawater itself is a good starting point, as seawater is not just a body of water containing salt. It's a complex mixture, a living body that can change at different locations. It contains different salts, it has dissolved gases, trace elements, suspended solids, and decomposed organic matter, together with living organisms, both large and small. And sometimes it's more the small ones that cause us an issue in terms of corrosion. Critically, the sea actually moves with great force, and the current or flow of the seawater can change dramatically, and this can have a large effect on corrosion. It's obviously not limited to natural movement and swells, and can also include the flow of water over the hull of a boat or a propeller, or even like the flow of water inside a pipe or tube. So, I mean, corrosion itself can be influenced by many factors within like the seawater. The oxygen content can be hugely important to certain metals and alloys, as many of the metals will form oxide films on the exterior of the surface to provide a superior corrosion resistance. And the oxygen can be affected by water depth, seawater velocity, pollution, and marine organisms. The flow rate of the water itself, how fast does it flow? Is it stagnant? Stagnant and polluted waters will have less oxygen content. So can you see any effect? And this could be a combination of factors. The salt water, the content of the salt in the water can widely vary between locations. For example, dissolved salt in the Baltic Sea is only around 7 grams per kilo, whereas salt content in the Persian Gulf is 43 grams per kilo. So there's obviously a huge variation between locations. Seawater temperatures. Temperatures don't just affect the rate of corrosion of materials, but it also affects the oxygen levels, with oxygen levels decreasing in higher temperature water. And again, temperature can vary tremendously, with temperatures ranging from 2 to 4 degrees C in the Arctic and in deep ocean depths, up to 29 degrees C in the tropics. And if you took a typical condenser outlet, temperatures can even reach 45 degrees C and above. Pollution is another major factor, and this can accelerate corrosion through lowering of oxygen, having other elements present that corrode the materials preferentially, etc. But we'll talk about that more as we go through. And also many metals can be subject to the attachment of organisms in the form of both micro and macro fouling. And you can see from the example on screen that this can completely cover the surface of the metal. So we cannot even see what's underneath, and worse still, we can't even see if there's any issues with any corrosion in the local area. So these variables are not straightforward, and not only will seawater vary from location to location, but individual places can show changes in temperature, biological activities, etc. during different seasons. So the complex nature of seawater makes it difficult to achieve realistic performance data from short-term testing in synthetic waters. So it's often necessary to carry out long-term exposure work in live seawater, and obviously carry those tests forward for as long as is necessary. So as you can see from the short introduction, the seawater is very aggressive in certain instances and is an unpredictable medium, with most metals and alloys being susceptible to degradation and corrosion in one form or another. Successful application of metals relies on proper design and maintenance, together with good design, fabrication, and good practice. So to do this, we must be aware of the types of corrosion materials are susceptible to and how to avoid potential problems. So this brief overview will describe the relative corrosion resistances of several different alloy groups used in seawater systems, with the main properties being covered, being resistance to flow, resistance to velocity, localized corrosion, stress corrosion cracking, galvanic behaviour, and marine organism attachment. We'll touch on these again later, but for information purposes, these would be the main mechanisms of corrosion that need to be considered. Some alloys are more susceptible to one form of corrosion than others, but they need to be taken into consideration as a whole, as if not, it may be the case that you inadvertently have a failure because marine structures and engineers' components are generally made up of more than one material. So we have to take into account each and every corrosion mechanism, and we'll briefly touch on each one as we go through the presentation. So where do we start? Basically, we'll start by going through some of the alloy groups, and we'll start with carbon steel and cast irons, as these are probably the most commonly used structural and engineering grades within marine environments. But as I'm sure you'll all know, steel and iron will rust. So why is it used? Well, steel can offer high strengths, good ductility, and it is also one of the lowest cost engineering materials available. And with proper protection, it can be used successfully. The corrosion of steel in seawater is primarily governed by the diffusion of oxygen in the water onto the steel surface. So going back to the previous slides, obviously the oxygen content plays a major part in the corrosion of steel and of cast irons. Research has been carried out in various locations on steels of various compositions. Immersed under quiet conditions, they can have quite predictable corrosion rates of around 0.1 to 0.2 millimeters per year. But they do sometimes suffer from pitting at several times this depth. So the localized corrosion again can be more of an issue than the overall loss of material around the component. So the other issue with steel in flowing seawater, the corrosion rate begins to increase, and at just 3 meters per second, a velocity often used in piping systems, the corrosion rate is approximately 0.75 millimeters per year. So already it's gone up like nearly fourfold on the previous figures quoted. But the corrosion rate can commonly increase to levels of 1 millimeter per year and even 2 millimeters per year in higher flowing waters. But in extremes, such as 40 meters per second, which can be achieved in areas of local high turbulence, a corrosion rate is possible of around 5 millimeters per year. So there is a vast difference in the corrosion rate of steels, but the corrosion of steel in marine environments is reasonably well understood. It has been well researched over the years, and can be managed by galvanic protection or coatings. Another common way of dealing with corrosion of steel is to over-engineer it and increase the thickness so that the design life can be increased. The last item mentioned on steel for today will be that it can suffer from accelerated low water corrosion, ALWC. This phenomenon is not so easily understood as other issues, and is generally found on dockside or pilings around the low water mark in the tidal area. It involves microbiologically influenced corrosion, and where sulfide reducing bacteria becomes active under deposits and marine growths, the corrosion rates can be as high as 0.5 millimeters per annum for this phenomenon alone. So all in all, there are a number of things to take into account when using steel. As I said before, it is quite well understood and it can be managed. So steel does corrode, but we can deal with it. The next group of alloys, would be the cast irons. Now, the cast irons have a similar corrosion rate to steel when talking about grey cast irons and spheroidal graphite irons. The traditional cast irons have like a graphite flake that sits in an iron matrix, and while the graphite is more noble material and doesn't corrode in seawater, the iron matrix is very susceptible to corrosion. So the iron can be corroded, leaving behind a deposit of graphite and silica and iron corrosion products. And this is a phenomenon known as gravitization. Generally, this type of corrosion is favoured by hot conditions and is often found in water boxes and valves in seawater systems. But at first glance, the surface may appear reasonably normal, just covered in rust, but underneath is a rather flaky, crumbly structure with a serious loss of material. And you can see from the image on screen, the darkened area around the edge of the cross section would be where the issue has occurred. and the lighter material is the more virgin material that was designed to use. So you can appreciate that carbon steels and cast irons both corrode in aerated seawater, but on the whole they're lower cost alloys. They may have higher maintenance and replacement costs associated with them, but not if successful protective measures are used, such as galvanic protection or a coating. So they do have a place in marine environments due to the economics, and obviously, as we mentioned in the steel section, if it's over-engineered, there can be no issue as well, even if there is some corrosion on the surface. So just to go on from the selective phase attack from the cast iron side of things, it's not a phenomenon that's limited to cast irons. So on screen you can see a valve stem made from 6040 brass that has shown signs of dezincification. Obviously the material was specified incorrectly and has failed as in operation, and it's due to the zinc phase corroding preferentially, as it wasn't as noble as the copper. However, if you were selecting a copper alloy for seawater use generally, then a corrosion or dezincification inhibitor would be selected, or again, we could look at galvanic corrosion, and we could make allowances that way. Or the image on the right shows a naval brass tube plate that's been in service for 11 years. This was specifically over-engineered, and you can see actual corrosion on the surface of the material. But because it was over-engineered, there's been no problem like with that particular component. And the component was designed correctly. So it's just understanding the corrosion method that could occur, and making sure that we select materials correctly, and select like proper design procedures to allow for like corrosion over time. Again, there's another example of selective phase corrosion and poor material selection. On the left, it's a stainless steel. It's a free machining stainless steel, grade 303. But no consideration has been made for corrosion resistance, and this particular grade uses sulfur as a chip breaker, and like this forms a magnesium sulfide within the microstructure, and like that phase is selectively corroded and eaten away, and even would be in normal tap water. On the right is a microstructure of a super duplex stainless steel, which is a more complex stainless grade that should theoretically offer much better corrosion resistance to more standard, cheaper grades of stainless. However, on this occasion, the material has been heat treated incorrectly, and the alloy has created a sigma phase that preferentially corrodes in seawater. So again, it shows the importance of selecting the correct material and taking into account all the material aspects. Going back to the cast irons, there have been a number of developments over the past 70 or 80 years, with other cast irons coming into effect, where additions of more noble elements have been made. So, for example, an alloy known as Ni-resist has additions of 15 to 25% nickel and small additions of chromium and silicon. And as the nickel content increases, the iron becomes more austenitic, hence the name Austenitic cast irons. And it actually reduces the corrosion rates compared to traditional grey cast irons or spheroidal cast irons. In fact, corrosion rates can be as low as 0.02 millimeters per year on this particular alloy. But again, the corrosion rates do increase with the flow rate and velocity of the seawater. And the alloys are often utilised more for larger workhorse jobs. They utilise the strengths. They're typically used for pumps and pump casings, and they can be used in copper and ferrous seawater systems reasonably satisfactorily. However, they can be susceptible to stress corrosion cracking as well. So whilst there are some improvements, there are other issues that again need to be taken into account during the material selection and design process. So we lead ourselves onto stainless steels, and these were developed around 90 years ago, and they were developed to offer a better corrosion resistance to carbon steels and cast irons. A stainless, by definition, is an iron alloy with more than 10.5% chromium, and these obtain their corrosion resistance from the formation of a protective chromium oxide film that forms on exposure to air. So where you can see the carbon steel on the left-hand side, when that is exposed to air, it begins to rust, and it gets a protective it gets a protective coating of rust that stabilizes the surface. Stainless steel gets a strong adhesive like film on the surface that's approximately 2 to 3 nanometers thick. And like this replenishes itself in oxygen if it is damaged. So it can repair itself, and in open seawater there's normally enough oxygen present to allow this film to repair and heal itself, so protecting the underlying metal from any corrosion. Stainless steels generally rely on the movement of seawater across the surface to prevent deposits and marine growth from forming, and it discourages local pitting, and if the water is flowing, and generally a velocity of around 1 meter per second. 1 meter per second is needed to prevent any pitting corrosion in seawater. The general corrosion rate of stainless steel is very low. It's around 0.002 millimeters per year. But this is achieved by enabling or ensuring that oxygen is available by the flow of seawater across the stainless steel surface, and this obviously helps maintain the protective film, and the material remains passive and immune from major material loss and corrosion. I mean, the film is actually maintained at higher velocities above 1 meter per second, and can even go as high as around 40 meters per second, which, if you remember, going back to the cast irons and these steels, this could show losses of 5 millimeters per year on that particular material. So it's a big step up, and a big improvement. The slides here show some 304 stainless, which is the top sample that's been exposed, and then below that is some 316 stainless, which has got molybdenum content in it. With the 304, the structure is still quite usable. I mean, especially after 57 years of exposure, it has got some signs of rust, but it's not disastrous. But more impressively, the 316, containing the molybdenum, has resisted light corrosion. So yeah, I mean, as long as we remain with a constant flow and plenty of oxygen, the stainless steels are capable of lasting for a significant amount of time. The stainless can actually be susceptible to pitting, and it can be found under exposed areas of metal, possibly under microfouling, or it could be that chloride levels are too high, or there's overchlorination, surface contamination, or surface inclusions being exposed. So, I mean, the problem of using stainless steels in seawater can often be the problem of pitting, and this can also be exposed by pitting attack under low velocity conditions, and in crevices and joins of material where the oxygen can't get to replace the protective film. Crevices or under deposit corrosion can also be an issue where the oxygen becomes locally depleted. An electrochemical cell is created where the film may have broken down, exposing the metal below, which then becomes anodic compared to the adjacent material. And like the steel will then corrode. The crevice corrosion occurs more readily than pitting in seawater and at lower temperatures. So higher levels of the same alloying additions are used to improve resistance to crevice corrosion as well as pitting. So molybdenum and nickel and chromium all add to the like the corrosion resistance. You can see from obviously the image on screen at the moment that it's an area that's been sealed by an O-ring or a nut in a confined area and suffered crevice corrosion. Or we have an image here where 316 has been used for a coupling, and where the O-ring is sat, there's been some crevice corrosion occur, Basically, this issue was cured by replacing the 316 with a 6% moly stainless steel, that then removed the tendency for crevice corrosion. Again, like if we go back to the previous image, this is where obviously the nut sat in the component, and you can see around the nut before it was removed that there is some rust, and then from that rust, when the nut is removed, you can see the crevice corrosion underneath the surface, and also on the parent material itself. So I mean, we can look at removing like the issue of crevice corrosion by using good practice. So it's always good to design design components, avoiding threaded connections, avoiding sealing tight crevices with welds, and making full penetration pipe welds. And alternatively, local improvements to crevice corrosion resistance can be achieved in areas such as flange faces by weld overlaying. And this weld overlaying would be done with more resistant high nickel alloys that would offer better crevice corrosion resistance. The crevice corrosion and pitting resistance is generally ranked on how susceptible they are, and it's generally accepted now that pitting resistance equivalent number of greater than 40 is required for high resistance to localized corrosion in ambient temperature seawater. And obviously the formula there is for the calculation of this. Alloys with a pitting resistance equivalent number of less than 40 often require cathodic protection still, and are sometimes galvanically protected by from other metals within the system to stop any crevice corrosion and pitting occurring. So it brings me now to the copper alloys, which is obviously more at home to myself. It's something that we do deal with on a daily basis. Now, the most common coppers used in marine engineering are coppers, but I mean, and aluminium bronzes, copper nickels. Now, these they have relatively simple additions to the copper matrix. So copper zinc makes a brass, copper tin makes a phosphor bronze, copper aluminium makes an aluminium bronze, and a nickel addition makes a copper nickel. So they are reasonably straightforward, but there are a lot of different groups with different benefits. We need to look at some of these in more detail. I mean, the benefits of copper alloys were recognised many years ago, back as far as like the 17th century, when the benefits of copper sheathing were recognised on ship hulls that kept them clean and enabled better manoeuvrability, and also gunmetals, i.e. tin bronzes that were used for cannon bodies on ships in olden times. But I mean, the copper alloys have actually been developed massively since those early days, with many groups of materials and the properties being developed. And again, this is a topic in itself, so I'll just touch the surface. The development of copper-based alloys has allowed a wide range of properties to be met, with strength levels available up to 1500 MPa, hardness values up to 45 HRC. The copper alloys can more than match strength levels associated with ferrous materials, such as stainless steels and nickel alloys and high strength steels. And also copper has as a whole offers low general corrosion rates in static seawater, approximately 0.02 millimeters per year, and has a little tendency to pit. However, they also offer a very useful resistance to flowing seawater, and can even handle moderately high velocities at intermittent periods. So to consider the relative merits of the various copper-based alloys, it's necessary to understand their behaviour in more detail, and in particular under flowing conditions, when stressed and exposed to seawater. Another aspect that is a benefit of copper and copper-based alloys is the castability and weldability, and also the manufacturing, which can influence the choice of the alloy for a particular application. Other properties include anti-galling properties, and an impairment of the attachment of seagrasses and hard shells, and shellfish. However, copper alloys can be subjected to higher corrosion rates when seawater contains ammonia and sulfides. So extended exposure to polluted conditions are probably not advisable for copper-based alloys. As you can see from the graphic here again, the flow rate does have an influence on which copper-based material should be selected, and whether like that material is then subjected to impingement attack, and at what velocity. The typical material for pipes and tubes are either aluminium brass or copper nickels, and as you can see from here, there are recommended guidelines for maximum flow per second, but this is for continual use rather than intermittent use, so it can actually increase in certain instances. But we should avoid sort of tight bends and localized obstructions, and then it avoids any turbulence and any issues with like crevice corrosion, etc. So both the 90-10 and 70-30 cupra nickels are successfully used for various seawater pipe work, and they're used in seawater condensers, heat exchangers, and pipe work in naval vessels and merchant shipping. The other areas, like the copper nickels can be used in fire water systems, and as I say, the intermittent use can allow for up to 10 to 15 meters per second in that particular application, and it can be successfully used. For if you were looking at boat hulls and you were sheathing a boat hull, then you can look at 12 to 19 meters per second. Or if you were looking for a nickel aluminium bronze, we could use this for a propeller, because they've got a high resistance to velocity, and they will like generally be used for their high resistance to cavitation and impingement attack. The The next group of alloys that we'll look at is like high nickel alloys. A couple of these include the nickel coppers, alloy 400 and K500. They show low general corrosion rates overall, and like this can be maintained at higher flow rates. The alloy 400 is approximately 2/3 nickel, 1/3 copper. The K500 is similar, but it has additions of aluminium and titanium, which when heat treated and precipitation hardened, the strength levels improve to nearly double that of the alloy 400, but retains the same corrosion resistance levels. They behave very similar to 316 stainless steel, and in that they have low corrosion rates at high flow rates. However, they can pit and crevice corrode in quiet conditions, and when they do, the pits tend to be flat and broad, rather than the undercutting pitting typical of stainless steels. Cathodic protection can be used when in contact with less noble metals, and this would enhance the performance of these alloys. But at velocities greater than 1 meter per second, same as the stainless steels, the surface would remain passive and offer a good resistance to corrosion. But you would need to be aware of materials in the same alloy system, as the nickel coppers are less noble than the nickel chromium molybdenum alloys and high alloy steels. So if they were coupled with these, then there could be issues. The alloys are typically used for fasteners, shafting, pumps, valve components, etc. And cast versions are available for impellers. The other significant group of nickel alloys, as just mentioned, was the nickel chromium molybdenum alloys. And these offer a very high resistance to corrosion, and in particular pitting and crevice corrosion. They've got a high corrosion resistance in both low and high flowing conditions, and like they can be used for critical items. However, they are expensive alloys due to the amount of nickel and also the alloying elements. Like their use is generally restricted to critical applications. These include alloys such as alloy 625 and C276, C22, and alloy 686. And like they provide a corrosion resistant material, but again, it comes down to economics and where the material's situated. The aluminium alloys, generally the 5000 series are preferred for seawater use, with a few of the 6000 series. The 6000 series offers higher strengths to the 5000 series. Now, the aluminium does actually offer a very low corrosion rate of less than 0.005 millimeters per year. But it is a galvanically active alloy, so if you are using it as a main alloy, then you have to ensure that the galvanic protection is in place, so that it doesn't become the sacrificial anode, because the passive film that protects the aluminium, it's not self-repairing. It can be enhanced by anodizing and coating, but yeah, it can cause issues if it does get damaged. And the last group of materials would be the titaniums. The titaniums are essentially immune to seawater corrosion and crevice corrosion below 75 degrees C. And in flow rates of less than 36 meters per second. Again, they're protected by titanium oxide on the external surface of the material. And any corrosion rates in static and reasonably flowing seawater are quite negligible. Interestingly, the titanium grades are also unaffected by chlorides, sulfides and chlorination. So even though they are quite a lot more expensive than other alternatives, their use becomes justifiable for more severe critical applications. But issues can occur where material loss from other alloys, because the titanium is so noble, you need to galvanically protect the materials that are in the system. Otherwise, the titanium would cause the other materials to corrode quite rapidly. So again, it's a balancing act between what is suitable for a particular application, what is coupled to, and where it's situated. So, I mean, we can actually recap on like the flow behaviour of the materials and how they perform under different flow rates. And as you can see, the carbon steels, cast irons offer quite significant corrosion rates under even low flow rates. The copper-based alloys offer a significantly lower rate of corrosion under reasonable flow rates, but when you get down to the higher flow rates, then this can cause problems with them. The 316 and the stainless steels, the nickel coppers, they have or their corrosion resistance systems rely on oxygen being fed to them, so they actually enjoy the like the higher flow rate. And the nickel, chromium, molybdenum, and the super stainlesses, titaniums, etc., again, don't have any real effect of increasing flow behaviour. The stress corrosion cracking is another issue that we've touched upon but not really gone into any depth on. Now, for stress corrosion cracking to occur, you need to have a susceptible alloy and a combination of a tensile strength and corrosive environment. So, for example, steels can stress corrosion crack in the presence of chloride at greater than 50 degrees C, or in the case of copper-based alloys, in the presence of ammonia. Failures due to stress corrosion cracking can be very unpredictable, and virtually all alloy systems can be susceptible under specific conditions. So it is something to be aware of and something to look at. The last corrosion mechanism that we've touched on and needs to be mentioned in more detail is galvanic corrosion. Now, this occurs when two or more metals are immersed in seawater. The seawater acts as an electrolyte, and a current flows between the two. And the more noble metal will act as a cathode and will have a lower corrosion rate than it normally would, while the less noble material would be the anode, and would actually corrode more than it normally would. There is a Galvanic series that's readily available for seeing which metals can be safely coupled with others, and generally, if they have a similar electrode potential and the surface areas don't differ too much, then they will be reasonably compatible. But the further apart the materials are on this scale, then the higher the rates of corrosion on the anodic material. So you can see that magnesium, zinc and aluminium on the table are all active galvanically and would be susceptible to corrosion if they were coupled with something at the more noble end of the scale, such as a bronze or a nickel alloy or titanium. So in that instance, galvanic protection would be necessary. Otherwise, you obtain situations like this where an aluminium ladder has corroded inside a steel casing, and obviously where the water rises and falls, there's been quite accelerated corrosion of the aluminium ladder. And another example would be like the galvanic corrosion of a duplex stainless, where it was used for a stainless steel flange. A graphite gasket was placed in between the flange, and as you can see from the area, the white area, there is galvanic corrosion has occurred, and there's quite a significant metal loss. So even something that is apparently quite noble in a duplex stainless, if it was coupled with the far more noble graphite gasket, then we would get issues. And another example is the galvanic corrosion of nickel aluminium bronze, where you've got a titanium tube. So the nickel aluminium bronze tube plate has corroded with accelerated corrosion, and that's due to like titanium tubes being much more noble than the nickel aluminium bronze, and the design of it all being wrong. So it just needs somebody just to understand the system, and try to design that out of any future work. So we can ensure that sort of galvanic corrosion is prevented by ensuring that materials have similar potentials, as in picture 2, or if you can put an insulator in between the two metals and the electrolyte just to stop the transfer of current, or if you can keep the electrolyte away from one of the substrates. So if you can keep the electrolyte purely on one metal, or put a coating on another metal, so that we don't create a galvanic cell. So but like the rule is that you do not coat just the anode alone. So I mean, I've tried to cover it. I know I'm running significantly late, so I do apologise. But I mean, there is a very good book that's available from Amazon. It's got no relation to myself, but I have used this for research myself. It's the corrosion performance of metals for marine environments. It's very reasonable and very informative. So if you do want any more information on such a large topic, then this is a good starting point. And if you do need any further details on copper or copper-based alloys, then please contact me on my email address. I mean, we have publications that are available to send out free of charge. So you know, please let us know if we can be of assistance. So thank you all for listening, and I hope I've covered as much information as possible.
Andy, wow, thank you for a stunning presentation. And as I said at the start, corrosion is such a deep topic, and I know you guys have a lot of resources available for surveyors, and I would certainly encourage them to maintain contact with you and your colleagues. We overrun just a little bit, but the next presentation, I know how long it is because it's a recorded video of Simon Ward. So if anyone's got any questions, we could certainly take a couple of questions. Any questions for Andy? In which case, you've obviously stunned everybody into silence, Andy.
Oh, that will send everybody to sleep.
Well, I shouldn't admit it, but we've just been pizza here in the office, so we're trying to keep ourselves going into this marathon. Thank you very, very much indeed. It's been a pleasure to see you online. Thank you for contributing, and we wish you well. Thanks, Andy.
All right, thanks a lot. Bye.